We're going to be continuing our investigation of linear programming. Now, last time we sort of started this process by thinking about linear equalities. And we went through sort of a series of questions. One was asking about existence of a solution. One was about arguing that we had a polynomial size solution in terms of the number of bits that were required in order to represent the solution. This is the good old AX equals B case. And then we started talking about algorithms such as Gaussian elimination. For actually constructing a solution if one exists, and sort of knowing that we can construct one of polynomial size. Okay? So this is taking us most of the way towards fully understanding the case of linear equalities. But there's one more thing that I want to look at, which is showing that there's no solution. So we've done these, but we didn't talk about this question, showing that there is not a solution to a particular AX equals B question, right? And sometimes there isn't one. So how would you know, your advisor just gave you a task, or your professor just gave you a homework problem to solve AX equals B, and you can't find an answer, right? In general, it's not really desirable to come back to your advisor and say, I can't find an answer, right? They don't like that. So you have to be more convincing. So how can you convince your advisor that there is no answer for you to find? Any thoughts on that? Yes? Okay, so but I will argue that this is a sort of trying to show exactly the same thing, right? You're trying to show that a particular matrix is not invertible. That's equivalent to showing that there is no solution for this AX equals B problem, right? Yeah? Good. So showing that the equalities produce a contradiction is sort of promising, right? You can say, well, look, I've got all of these different equalities, and they can't all be solved at the same time. But again, I'm just saying I can't find a solution to all of these equalities at the same time. How do I make that convincing to somebody? Right? I can't just say I'm unable to find a solution to these equalities. Yeah?
You can show that some of the columns are linearly dependent.
Okay, so you can try and show some sort of linear dependence. And this is sort of an important shift, right? To sort of say, I cannot successfully execute the algorithm for such and such. That's hard for somebody else to check, right? They would have to go and try and run the algorithm themselves and run into the same problem that you did. If you want to sort of, if you instead are able to show some sort of, take this linear combination and look, it produces a contradiction, that gives an algorithm that somebody can execute and read off an answer at the end, right? So technically, the way to show that there's no solution might be to just, tell somebody, well, try running Gaussian elimination, and it's not going to work. But it's better if you can give a concrete certificate. Something that can easily be checked in order to show that in order to demonstrate that there is no solution. Right? And I'm going to show you one such certificate. I mean, there are many ways to describe this, but this is a convenient one for what we're going to be doing later. So the claim is that, let's see how to say this. That there is no AX equals B solution if and only if there exists a y such that ya equals 0 yb is not equal to 0. Okay. So notice, you're right, A is a matrix. It had n rows, and so x was an n-dimensional vector. A has m columns, okay? And, sorry, I said that backwards. X is an n-dimensional vector. That means that A has n columns, but it has m rows, which are sort of correspond to the constraints that we're thinking about. And so y is going to be an m-dimensional vector. Okay. So another way to look at this is what we might call a duality, right? That either there's a solution to ax equals b, or there is a solution to ya equals 0, but yb is not equal to 0. Okay. And so this gives us a very convenient way to demonstrate to somebody that you can't solve the problem, right? We just show them y, and they just do a matrix multiplication and check whether it is indeed the case that we have these two conditions. Okay. So how do we prove this? Well, this question asking for an A, we want to start from the, we need to prove it in both directions, right? So let's suppose, whoops. Let's suppose we have a solution in ax equals b. Okay. I want to prove then that there is no y satisfying these two conditions. Yes?
Sorry, for the yb is not 0?
Yes.
Does it have to be all of them are bigger than 0 or all smaller?
No, it just has to be that yb in its entirety is not the 0 vector.
Okay, so what are these?
Not equal, right? Sorry, I guess I've been doing too much programming lately. Is that clear?
Yeah.
Okay. Wow. Okay, so suppose we have an ax equals b. Yes?
Is that element-wise multiplication or the dot product?
That's the dot product. We don't do element-wise multiplication in this class.
Zero?
What was that? Oh, thank you. Yes, this is all 0. Okay. All right, so suppose we have this solution, ax equals b. I want to demonstrate that in that case there's no y. How do I do that? Well, let's start with, I want to show that you can't satisfy both of these. So in particular, I have to show that if you satisfy this one, you can't satisfy this one. Okay. So now let's suppose that we have a y such that ya is equal to 0, and this is the 0 vector. Okay. How can I conclude that you do not satisfy this? Well, yes, go ahead. Just multiply both sides by y, right? So I have this ax equals b. So I can conclude that ya times x is equal to b times x. Is equal to 0 times x, right? But what's ya times x? Well, we said that, So we said that ax is equal to b. So here we have yb. And that's going to be equal to 0. Okay. So y equals 0 will imply that yb equals 0, and so you will not be able to satisfy both of these conditions at once. Okay. But now suppose the converse. Suppose that there is no x such that ax equals b. This is a harder place to work from because we're sort of working with a, we can't say here's an x, let's work with it. We have to say no x will work. So the way to think about this is that the statement that ax equals b is a statement that the columns of A, there's a linear combination of the columns of A that produces b. Right? So the statement that ax equals b means the columns of A span B. So if we tell you that there is no x such that ax equals b, well, we can consider the subspace consisting of all the points AX. And that set of points does not include B. Right? Okay, so pictorially, I can go and draw my subspace. Here's AX. Right? And since I only have 2 dimensions to work with, I'm going to have to make AX be a 1-dimensional subspace. And here's B. And from this, and we've sort of argued that B is not in the subspace. So now from this picture, we want to argue that it's possible to find a Y. Right? And we want a Y that has, right, dot product 0 with all of the columns of A. So it needs to be perpendicular to this subspace, but has a positive or negative dot product with B. Can we do that? Well, yes, right? I can just take this point B and decompose it into something that is perpendicular to A and something that is parallel to A. Right? And I can generalize this to any dimension that I like. Right? The thing to notice is that the matrix A, the columns of A are the things that are perpendicular to the set of points AX equals 0. Right? That's the definition of the subspace. So if I decompose B into something that is parallel to the columns of A and something that is perpendicular to the columns of A, right? Then I can get something that, whoops, wrong notes. Right? So then the part of B that is perpendicular to the subspace satisfies YA equal to 0, but YB not equal to 0, because B is off of the subspace. Okay. Yes? What was that?
Is Y the part?
Yes. So I'm going to say Y equals the part of B that is perpendicular to the subspace. Okay. So you project B onto the subspace, you subtract out that part. Whatever's left is going to satisfy the conditions for Y. Okay. Is that clear? Okay. So this gives us a nice condition, right? It tells us that there is a Y. So if we want to show somebody there is no solution, we just give them this Y. But can we give them this Y? Do we know that this Y can be written down in a finite number of bits? Or even better, in a polynomial number of bits? Yeah? Good. So you can look at it from the algorithmic perspective, right? That we're solving a system of linear equations just like we did last time. I don't even actually have to go to the projection, right? So notice that YA equals 0, YB not equal to 0, oops, feasible, right? If I can solve that, then certainly by rescaling, then I can solve YA equals 0 and YB equal 1. Right? Whatever solution I have that's not 0, I can rescale Y in order to produce a solution of value 1. But now I can just rewrite these as a set of linear equalities, right? And we showed last time that this has a polynomial size solution. Right? polynomial number of bits in the answers that are involved. Okay. So now we've really kind of and of course, because we've written it as a system of linear equations, we also know how to solve it, right? We do our Gaussian elimination or whatever, and we get our answer. So this kind of completes the story of linear equalities. Okay, we have a sort of a complete characterization of when is there a solution to ax equals b, and conversely, if there isn't a solution to ax equals b, we have a characterization of a witness for the non-existent. Right? We have a witness when there is a solution, namely x. We have a witness when there is not a solution, namely y. And we can construct either witness in polynomial time, and that resulting witness has a size which is polynomial in the number, which has a polynomial number of bits. So that's kind of the end of the story for for systems of linear equalities. Any questions about that before we move on? Okay, so we're going to move on and start thinking about LP. So what's different with LP? Well, all we'd have to do is go and sort of replace that equality with an inequality, right? Unfortunately, that makes everything much more complicated. And in fact, I don't think we're going to see any algorithms today, because just looking at this very first question of sort of characterizing the solutions and arguing that that they have polynomial size is going to take up most of this lecture. Okay? But we're going to, and so we're going to work through the same process, right? We're going to sort of try and understand what the solutions look like. We are going to then argue that those solutions can be written down. They have polynomial size, so there's at least some hope of a weakly polynomial algorithm. Okay? And then maybe we'll get around to actually giving an algorithm, a finite algorithm. Okay? Polynomial time algorithms we're going to have to wait for. Okay? So in order to take that first step of characterizing the solution, we're going to need to talk about the geometry of linear programming. Okay. So we're going to be working a lot with pictures. So remember, we talked last time about our canonical form linear program, which asked for a minimization of Cx such that Ax is greater than or equal to b. Right? And thinking only about intuition here, right? Ax equals greater than or equal to b is sort of an intersection of half spaces, right? A single constraint Ax equals b defines a hyperplane, and we're saying one side of that is OK. So we're going to take a whole bunch of these hyperplanes, and we're going to intersect them to get a feasible region. Okay? And our objective function is going to point in some direction. And so intuitively, what we want to do is just move as far as possible in the direction of that objective function until we hit something that keeps us from going further. Now, another perspective is the standard form, where we write min Cx such that Ax is equal to b and x greater than or equal to 0. And algebraically, this is exactly the same. We showed that last time, right? But pictorially, the perspective is somewhat different. And this one, you kind of need 3 dimensions to draw a nice picture of. Let's see, do I want the... I don't know if I can draw in 3 dimensions. Let's see. Yeah, so essentially, the Ax equals b constraints can be thought of as a lower dimensional hyperplane. Okay, so in this case, it's a 2-dimensional plane. And it's bounded by the axes of the higher dimensional space within which you're thinking. Right? So here I've drawn, although you obviously can't tell, a 3-dimensional space with a 2-dimensional space that has been sliced and is sort of bounded at the 3 planes that correspond to the axes. Okay? So this is a slightly different picture of linear programming. It's actually all the same, right? If I wanted to take this one and turn it into this one, what would I do? Sorry, that was probably a completely opaque question. What I have here is a two-dimensional object of feasibility. So what I can do is I can change my coordinate system so that I'm just looking at the two dimensions that this hyperplane defines, right? And within that coordinate system of two dimensions, which is just a linear transformation, I'm going to have a picture like this one, where I have a triangle. Okay? And conversely, when I add slack variables, what I'm really doing is taking one of these full-dimensional shapes and flattening it out into in a higher dimensional space. Okay? So two different pictures, same fundamental meaning. In either case, we are going to define these shapes that are defined by these constraints. These intersections of half spaces are called polytopes. Okay. And with the ax greater than or equal b constraints, you'll often have a full dimensional polytope. That's kind of the way I like to think about it intuitively. But with the standard form, you'll have a polytope which is not full dimensional in the space where it's represented. Okay. Some other definitions. We're going to say that these polytopes are bounded if they fit in a box, a finite box. And so both of these polytopes that I've drawn are bounded, right? In other words, there's some maximum value for all of the numbers that are attained within this polytope, all of the different coordinates. Yes?
And the box is an n-dimensional space.
That is correct. It is an n-dimensional box. Another thing to notice is that polytopes are what are called convex sets. Namely, if x and y are both inside of the polytope, then the line from x to y stays inside of the polytope. So lambda x plus 1 minus lambda y is in the polytope for lambda between 0 and 1. Okay, so as I move along the line from x to y, I stay inside the polytope. Okay. Is this obvious? Or, sorry, that's a very bad question to ask. To see this, notice that a single hyperplane, a single constraint can be shown to be convex, right? If x satisfies the constraint and y satisfies the constraint, then this line from x to y is also going to satisfy the constraint. And so now you just take the intersection of all that in order to infer convexity of general polytopes. In fact, you can also show the opposite, that if you have a convex set, you can always create it by intersecting a bunch of these hyperplanes. If the convex set is curvy, then you have to use an infinite number of them. Okay? Whereas if it's nice and flat everywhere, then that corresponds to using a finite number of them. Okay. So now that we have these pictures, let's talk about characterizing our optimal solutions. So remember that, unlike the linear equalities case, we're trying to optimize some objective function now. And it would be good to sort of narrow down the space of possible optimum solutions to one of these problems, or to talk about a canonical optimal solution so that we can focus our attention on finding a solution that satisfies certain criteria. So let me ask that as we look for a canonical solution to an LP. So here's my LP. Where can the optima be? maybe anywhere in this polytope? Yeah. Okay, so it seems pretty clear that the optima need to be on the boundary of the polytope, right? Why is that? Why can't the optimum be in the center of the polytope? Yeah?
So, well, if your cost function was perpendicular to the plane.
Degenerate cases. Let's not worry about that. Okay. So yes, if your cost function is 0, then every point in the polytope is an optimum. But let's look at a non-degenerate case. Yeah?
Is it because the cost function is linear?
Exactly. Right, the cost function is linear. So if you're somewhere in the middle of the polytope, right, if you're inside the polytope, it means you can move in the direction of the cost function. And if you move in the direction of the cost function, or sorry, are we doing a min? Yeah, if you move away, if you move opposite the direction of the cost function, then you're improving your objective. Right? So we don't have to, we've made a dramatic simplification, right? We've ruled out an infinite portion of the polytope. Right? And we're left with only this tiny bit on the boundaries. Okay? But I claim we can do even better. Okay, can the optimum, or when we're looking for an optimum, do we have to look everywhere on the boundary of the polytope? Yeah? Corners. Okay. So it seems like we should be able to say something about the optimum always being at a corner. Okay. But that requires us to define corner. Yes?
Could it be along the entire edge?
Yes. So this is an interesting thing to think about. It is certainly possible, right? If this were my objective function, then this entire edge would optimize the objective function. But, yes?
In that case, some of the things that we have not yet defined, corners, would also be.
Exactly. The point is that in that case, there is an optimum at the corners. Right? It is possible to have optima at other places, off the corners, but there always, it appears, is an optimum at a corner. So that would tell us that we only need to look at corners, which even further reduces the space of possibilities by an infinite amount. Right? So this is great progress. Right? 2 orders of infinity struck down. Okay? But we have to define corner. So what is the definition or characterization of a corner of a polytope? And I will hint to you that there are 3 correct answers. Okay, so you have 3 times as many possibilities, 3 times as much chance as usual to be correct. Yes? Good. So in this picture, a corner is an intersection of 2 hyperplanes. What would be the appropriate generalization of that, since we're working with n-dimensional linear programs? Yeah?
In an n-dimensional space, the intersection of n hyperplanes.
Good. So that is the definition that is referred to as a basic feasible solution. If you're given a linear program, a basic feasible solution is defined to be one where all the equality constraints are met. Actually, let me put it this way. A basic feasible solution is a feasible solution. Right? So that means that, well, it means what it says. In particular, it means all the equality constraints are tight, and all of the inequality are met exactly. And all of the inequality constraints, the point is on the proper side of the inequality. Also, n constraints are tight. But we have to be a little bit picky here in order to deal with annoying people like the one who suggested having a degenerate objective function. N linearly independent constraints are tight. Oh, shucks. Somebody asked me to write bigger, but I haven't adjusted my length yet properly. So this seems like a good definition of corner. Okay. Right? The n-tight linear constraints kind of uniquely specify the point, right? But it's not the only natural definition of a corner. Any other suggestions? Yeah.
It's a point in your polytope that's not a linear combination of linear.
Great. So a vertex is defined to be a point that is not a a feasible point that is not a convex combination of others. Okay. Now we've got one more. What else defines a corner? Yeah?
Unique optimum for some convex.
Good. So an extreme point is a point that is the unique optimum for some objective. Okay. So this also makes a lot of sense, right? That both of these additional definitions, right? So being a vertex means you kind of stick out the farthest in some direction. So it sort of fits this unique optimum condition. And because it's sticking out the farthest, there's no way to make it a combination of two other things because those things aren't sticking out as far. Okay, so now we have three sort of natural definitions of corners. Fortunately, they're all the same. Okay, so we will shortly prove that, or sketch proofs, that these are all equivalent definitions. But before we do that, let's do this key lemma, which is that any standard form LP has an optimum. Any standard form LP with an optimum. I can certainly define infeasible ones. Has one at a basic feasible solution. The statement clear? Right, saying you only have to look at basic feasible solutions for your optima. So how do we prove it? Well, the usual proof by contradiction. So suppose we have an we have an x that is optimum, and it is not at the basic feasible solution. And let's see where that takes us. So what does it mean that x is not a basic feasible solution? Well, just working from the definition, what does that tell us?
The span of the dimension of the span of the tight constraints it satisfies is less than n.
Right, or sort of, I think more concisely, there are less than n tight constraints. Or linearly independent tight constraints. Okay, so forgetting about the linear independence bit for a minute, which is just to deal with the hecklers. What can we say about if we have less than n tight constraints? holding on to x. What does that mean? Yeah? It means that there's some degree of freedom for x, right? So this implies that there is a feasible subspace, that the set of points that satisfies these constraints or tight for, rather, tight at these constraints, has dimension greater than 0. Right? In particular, there exists a line through x obeying all these constraints. Right? So what can we say about that line? Okay, so we're on x. There's a line through x that continues to satisfy all of these tight constraints. So if we start at x and move along this line, at least for a really short distance, what's going to be true? Yeah?
So if you go in one direction and the optimum decreases,
Mm-hmm.
then you guarantee that it's going to increase in the other direction.
Good. So we know that we can move in on this line, we can move in either direction and stay feasible, right? We may not be able to move indefinitely in either direction. We might hit another constraint, but at least for a very short distance, we're feasible. Okay. So now as we look at what happens when we move back and forth on this line, well, we have this linear objective function, right? So let's move from x on the line, okay, in one direction or another. Right? What can happen to the objective function? Well, it's a linear objective function. And so it either increases or decreases or is unchanged. Those are the only things that can happen, right? Now, is it possible for the objective to decrease as I move along the line? You're shaking your head. Why not?
Because x was an optimum.
X was optimum, right? So I can rule out the decrease because x was optimum. Okay. Is it possible for the objective to increase as I move along the line? Yeah?
No, definitely just go the other way.
Right. So if I increase, I can reverse directions. And then I'll be going in a direction where it decreases. So it's not possible to have an increase because then there would be a decrease. So in neither direction does the value of the objective change. So in fact, this entire line is optimal. Okay. Now since this entire line is optimal, what should I do? Well, I can just head out in either direction along the line, right? Can I do this forever? We're bounded, right? So let's consider moving on this line. What's going to happen as I move on this line? Well, I can watch the coordinates of x, right? Some of them are going up, some of them are going down. But at a certain, right? And in one of these two directions, actually, I can guarantee that some of them are going down, right? They can't all be going up in both directions, right? Except, you know, that was my dad who walked uphill both ways to school. But so you haven't heard that one before? Wow. OK. So in one of these two directions of motion, at least one of my coordinates will be decreasing. Yes? So let's move in the direction of a coordinate decrease. Okay. Well, as the coordinate decreases, what eventually happens if the coordinate is decreasing? Yeah?
It's 0.
Until it hits 0. What happens when it hits 0? Yeah?
You get one more active.
Right. So now I have one more tight constraint. What should I do now? Huh?
Use induction.
Induction, or just repeat. So I'm just going to repeat this process until I have n tight constraints. And notice that throughout this process, I did not change the value of the objective. So I will finish with a point that does have n tight constraints and has exactly the same value as I had before. Right? So I have found my optimum at a basic feasible solution. Yes?
So when you like move in the direction of the coordinate decrease, could you also hit like another constraint when you hit 0?
Well, in standard form, we only have two kinds of constraints, right? We have ax equals b, which is always satisfied, right? And is satisfied by all of the points on our line. And we have the x greater than or equal to 0 constraint. So those are the only ones that can be loose and can then become tight. In the general case of linear programming, you're absolutely right, right? You move until you hit some tight constraint, right? So I've proved this for standard form because we know that we can transform everything into standard form. In fact, you can prove it for any bounded linear program, regardless of its form. Okay. Now, if you look a little carefully, we've actually proven something a little bit stronger, which is useful in the algorithms that we're not going to get to today. Because what we've given here is an algorithm, right? We've constructed a basic feasible solution from any point, right? So what we've actually proven is that given any feasible point can be transformed to a BFS of objective no worse. Okay. Right? So we can take any point inside the polytope and we can move to a basic feasible solution without sacrificing the quality of our objective function. And that will be useful later on. Okay. So this is pretty nice to prove that any point, sorry, any LP has a solution, or sorry, any standard form LP has a solution at a basic feasible solution. Okay. Now it's worth noticing that this is not necessarily true for general linear programming. Okay, I can exhibit a linear program that does not have an optimum at a basic feasible solution. Okay. For example, I can create a two-dimensional linear program where I say minimize x such that x is greater than or equal to 0. Okay. Now notice there's also a y here. I just didn't write it into the constraints. So this is the only constraint, right? And the minimum value of it is anything on the x-axis, right? But the entire upper half plane is feasible. So this is a polytope that has no basic feasible solutions, right? Why did that happen? Well, because this polytope is unbounded, right? It doesn't have it never runs out, so you can never run into corners. Okay. However, any feasible and bounded LP has a basic feasible solution. Okay. All right, so that's a nice step in the direction that we want. Yes?
Sorry, so in this lemma, where did we use the boundedness? Did we use it in where?
Good question.
Right.
Where did we use the boundedness? Sorry, what was that?
Was it in that we can write it in standard form?
No, you can, let's see. You can always write an LP in standard form, right? We We proved that last time. So where did we use the boundedness? Go ahead. It's this knowledge that we stop at some point, right? And so where did I kind of assert something that relied on that? Yes?
It's that it has an optimal solution. Any standard form LP with an optimum.
Right. So that is a correct statement. Any standard form LP with an optimum is going to satisfy boundedness. You can define a standard form LP, I think, let me think about this. AX equals min AX equals B, X greater than or equals to. No, you can do the same sort of trick with a standard form LP, right? I mean, this is a standard form LP, right? Right. So that's the point, right? So you can write a standard form LP that does not have a basic feasible solution. No, it has an optimum. It has many of them, right? Every point on the x-axis is an optimum. Yeah? Oh, I'm sorry. You're right. X greater than or equals 0 is not standard form, right? So so the standard form part. No, wait. X greater than or equals 0 is in standard form.
No, but you need y greater than or equals 0 if you have an implicit y.
Oh, yes, that's the point, right? So this is missing y greater than or equal to 0, and so it doesn't have and so it's not standard form. If I add the y greater than or equal to 0 constraint, then I immediately get my optimum vertex. But the problem is that since this is unbounded, right? Over here, it was this notion of moving until things hit 0. Yes?
I think the moving to 0 works if it's in standard form because you can always, like you said, you can always go down.
Except that here the problem here actually is that I run out of constraints to use, right? So if right here I only have one constraint, I can force that constraint to be 0. But I have no other constraints I can then move on in order to make another coordinate tight. Okay. All right. So if we have a bounded LP, we have a BFS, but we have the same question as before. Is it possible to write down the BFS?
Sorry,
Yeah.
I might have missed it. Where did you use boundedness in the proof?
Where did I use boundedness in the proof? Well, I think that a standard form LP is always going. No, wait. A standard form LP is going to be bounded from below. Let me take that one after break so that I can figure out a sensible answer, okay? But working from this idea that we can find a basic feasible solution, how do we know that we can write it down? What if it's irrational? So can we argue that in fact this basic feasible solution has a rational representation or involves a finite number of bits? Yes?
It's the solution to a system of n equations.
Great. So notice that the BFS is the solution to n tight constraints. Right? Which, of course, can be written in the form AX equals B. Yes? And we saw last time that it has polynomial size. So that's great. That means that that it's possible to write down the answer, right? There is an optimum to any linear program that can be written down. That's a good first step. This actually shows us even more, right? It suggests our first linear programming algorithm. That completes in finite time. Okay. So knowing that the solution is at a basic feasible solution, how do you suppose we could find it? Yeah?
Check all basic feasible solutions.
Try all basic feasible solutions. Why is that a finite algorithm? Because there's a finite number of basic feasible solutions. How many can there be? Right. So we have m constraints. We can guess which n of them are tight. right? And so there are m choose n possibilities. So fleshing out the algorithm, what do? Well, we check every set of n constraints. We check if they're linearly independent, and if so, we find the single point that satisfies all of them. And then we check if it's feasible, and we calculate its optimum value. And we could calculate its objective value. And we just keep track of the point, the basic feasible solution that has the smallest objective value. At the end, we're done. We have our we have our optimum solution to the linear program. Right? And all of these calculations, as we saw last time, because they're matrix inversions, can be done in polynomial time and involve polynomial-sized numbers. So the algorithm is finite and, in fact, has a running time of m choose n. So notice that, in particular, in fixed dimension, right, two-dimensional linear programming, we have now shown that it can be solved in polynomial time. Right? Or even three-dimensional linear programming. Or 10-dimensional linear programming. It can all be solved in polynomial time. So that's nice progress. That's a nice step. And in fact, this was kind of what was achieved in the 1940s. Right? The sort of early study of linear programming was derived algorithms which essentially have this character. They're exponential time searches over all the possible basic feasible solutions of the linear program. Turns out in practice they can be made to work much better than that. Which made a big difference. But from a theoretical perspective, this is what the algorithms of the 40s were doing. Okay. Yes?
So if n is constant, m choose n can still be really large.
Yes, but the total is just m to the n power. And so as long as n is constant, that's a polynomial. Right? Remember, you're in a theory class now. Okay. All right. Other questions about this algorithm? OK, let's take a short break, and then I'll tell you some more. What we've proven here is that every standard form LP has a BFS. Right? And the reason for that is that every standard form LP is bounded. Right? And that's actually why we like to work with standard form LPs, is that they are bounded. Now the question is, what about all the LPs that are not bounded? We showed last time that you can transform them into standard form LPs. But that transformation is actually a way of making the LP bounded without changing fundamentally the structure of the solutions. Okay? So this is why we like standard form LPs. And right, so like with this LP over here, this is an unbounded LP. The process of transforming it into a standard form LP will give you one that is bounded. Okay? Or I believe that's true. Yes?
But did you just take the positive ordinate?
Yes, so right. So that's not bounded in the sense of being bounded in every direction. But remember that the standard form LP wants to minimize an objective, right? And so, oh, no, what am I saying? Right? We can always use a negative objective, so we can go out in the opposite direction. So if there are no constraints aside from the positive orthant, then we get an unbounded standard form LP. All right, let me put this on deck for. Right, that doesn't have an optimum at all, right? It's sort of going on. If you can show that if it has an optimum, then it's going to have to be bounded. But instead of working this out in class, I'll sort of take care of the details of it in next lecture. Okay? By which point I'll have it all carefully worked out. What I want to focus on now, let's see, I have half an hour. What am I going to do in half an hour? Well, I could figure out how to prove that standard form LPs are bounded, but yeah, let's quickly look at these other two characterizations of corners. This will be useful later. So first, let's talk about vertices. So remember we had this notion of a vertex, something which is not a convex combination of other feasible points. Okay. So I want to prove that vertex and basic feasible solution mean exactly the same thing. Okay. And it's not very complicated, right? So if I have a point which is a convex combination of feasible points, right, then let's say it's a convex combination of y and z. Well, then the line through y and z is a feasible line, right? All the points on that line from y to z are feasible, right? So we don't have n-type constraints at x, because if we had n-type constraints at x, then this line would not be feasible. Okay. And it works the other way around too, right? So conversely, if I have less than n-type constraints, that lets me draw a line through x. And that gives me, by taking one point on each side of the line, y and z that combine to x. Yes? So if a point is not a vertex, then it is not a basic feasible solution, right? If a point is not a basic feasible solution, then it also is not a vertex. Okay. Now we also had this notion of an extreme point, which is the unique optimum of some objective C. And I want to show you that an extreme point is also the same as a basic feasible solution. Okay. So one of these directions is actually quite easy to prove, given the technique that we used for analyzing a basic feasible solution. Okay. So suppose that I am the unique optimum for a particular objective function, and I now try to apply the reduction that I did here for basic feasible solutions. What's going to happen? Right? I am at the unique optimum point for this objective function C. Okay? And now I'm going to do this this process, this iterative process for getting to a basic feasible solution. So what happens? Yeah? I can't move. How come I can't move? There are no other optima, right? The whole point of the argument over there was that I could move along a line of optima. So if my optimum is unique, there can't be a line of optima. Okay? Which must mean I'm already at an intersection of n-type constraints. Okay? So if I am extreme, that implies that there is no line of unchanging objective and the only way there can be no line, no way for me to change, is if there are n-type constraints. In other words, I have a BFS. Okay. So all that's left is showing that from a BFS, I can get to an extreme point. Okay. And this is kind of the trickiest of them. I have to show, since I have a BFS, I need to exhibit an objective function for which that BFS is the unique optimum. Okay. So you can do this in general on polytopes, but it's easiest to see in standard form. Okay. So let's start with our BFS in standard form. What is it? Well, it's tight for all the ax equals b constraints, and it's tight for some of the x greater than or equal to 0 constraints, right? So let's let t be equal to the tight x greater than or equal to 0 constraints. Okay, so those are the constraints where my point is actually equal to 0. Okay. So I want to make this point be the unique optimum for some objective function. what is that objective function going to be? Well, what distinguishes this point? This is the point where all of these constraints are 0, all the constraints in T. So if I want it to be the unique optimum, what sort of objective function should I use? Yeah?
The sum of those x's.
Exactly. So let's let the objective be the sum over I in this tight constraint set of xi. Okay. So let's think about any point in the polytope. Okay. If it's not this point, this basic feasible solution, well, it still satisfies all of the xi greater than or equal to 0 constraints, but it has to be loose on one of these constraints. Right? So on one of these constraints, the point has a value of xi that is positive. Okay? So my BFS has value 0. Right? Any other point is loose on some xi, which means that it has objective value greater than 0. So I'm done. I've proven that only my basic feasible solution has value 0. And so it is the unique optimum for that point, and so it's an extreme point. Okay. So now we know that all three of these corner characterizations are the same. Oh, I should say, here I proved it just in standard form. You can generalize this to any polytope. You use an objective function, which is the sum of the normals to the constraints. And you can argue the same way. Okay? So this proves that they're all equivalent, and so now we will use them equivalently, whichever one is most convenient for our analysis. Okay. So remembering where we are now, we have an algorithm which runs in finite time for finding a solution to any linear program in standard form, and therefore to any linear program. And we know that we can write down the answer with a polynomial number of bits. Yes?
So in the canonical form, there is a degenerate case.
Sorry? The what?
In the canonical form, there is
Yes.
a degenerate case where a corner can be the intersection of n plus 1. It's like the top
Yes.
of
Yes. Well, so that's why this sort of basic feasible solution is defined in terms of n linearly independent constraints. And that solution may actually be an intersection of more than n constraints. Right? But they won't all be linearly independent. Obviously, they can't be. Okay? All right, so what's our next step? Now that we've proven that you can write down the answer and that you can find it in a finite time, the next step is showing that an answer is optimal, or that you can't find a good, that there's no good answer. Okay? So how do we decide if a solution is optimal? Okay. So that actually suggests one direction we could go, which is to a decision version of the linear programming problem. Right? Is there an AX greater than or equal to B with value Cx less than some Q? Okay. Let me say D just to be consistent with my coefficients. Okay, so we can set a threshold and ask the decision version of the problem. Right? Often decision versions of problems are easier or a good starting point for thinking about optimization versions. For one thing, you can just switch. You can use binary search on a decision version in order to get optimization. Unfortunately, we're going to show that this is equivalent to standard linear programming. So that's not going to be a useful simplification to tackle. Okay. But let's ask about the sort of NP question. So before we, sorry, we actually I should say that we've shown that LP is an element of NP. Right? We have a non-deterministic polynomial time algorithm for addressing this decision problem, right? If there is a solution that has value Cx less than or equal to d, we can guess it, and we can check it, right? We just check feasibility, check the value of the objective, and we're done. Okay. So from the sort of simplification or breaking down in pieces, a natural next question to ask is whether LP is in co-NP. So if there is no solution better than D, can we demonstrate that? So this is the analog with our linear system problem of showing that there's no solution to the linear system, right? And if you think about it, this is saying, can we show that a particular linear program is infeasible? There's no solution, right? Which is like asking that there's no solution better than a given value. Okay? So that's what we're going to try next, is working in that space of problems. In particular, we are going to try to construct a lower bound on the value of this objective function, min of cx, such that ax equals b and x is greater than or equal to 0. So we're starting with some standard form linear program. Okay. And we are going to try to say, well, I can't find exactly the solution, but here's a lower bound. And we're going to use the tricks that we learned in high school for solving linear systems, right? If you're given a linear system in high school and you're told to solve it, what you generally do is play around with taking combinations of the equations to try to cancel things out and get an answer on the other side, right? We're going to try and do the same thing here with our inequalities. Okay. So let's try multiplying and adding constraints. Okay. So I've got these constraints, a1 times x and so forth equal to b. In particular, let's multiply the constraint that aix equals bi by some yi, and then add all of them. Okay. So what happens when I multiply all of these constraints and then add? Well, I get a new statement that says that y times ax is equal to y times b. Right? All right. Now, suppose that I can find some c such that ya is equal to c. Okay, this is kind of looking back to the linear systems perspective. So if I know that ya is equal to c, and also that yax is equal to yb, well, then I can conclude that if I combine these, right? If I take this and sort of multiply both sides of this by x, I find out that yax is equal to cx, right? Is equal to yb. Right? But that's very nice because cx is our objective value for this linear program. So if I'm able to find this magic c such that y is equal to c, then what have I actually shown? I've shown that every feasible x has the same objective value, right? Every x has the same objective. So they're all optimal. Right? So that's sort of a weird special degenerate case. Okay? If I can do exactly the right kind of manipulation of my equations, I end up discovering that everything has the same objective value. Yes?
You mean if you could find y such that y equals c?
Yes, sorry, typo. We were given c. It was part of the LP. Right? Did that make this much clearer now? Okay. Now, in general, we can't do that, okay? But sort of we can aim for something looser, okay? If we ensure that not that y is equal to c, but that ya is coordinate-wise less than or equal to c. All right? Then we can conclude that yb, which is equal to yax, is less than or equal to cx. Okay? So again, we're working with this combination of linear equation of constraints. But now we're going to make sure that we obey c as an upper bound on each of our combinations. And because we take this as an upper bound, we can conclude, since we're less than or equal to c in each constraint, in each coordinate, that the resulting yb will be less than or equal to c times x. Okay. Why is that useful? Why is it useful to be able to say that yb is less than or equal to cx? What was our original goal? A lower bound on what? We wanted a lower bound on the value of the objective function. Well, we just found one, right? Right? So this is true for all x. yb is a lower bound. Now, why was it important for me to make to sort of enforce ya less than or equal to c? Do I get a lower bound regardless of, can I just pick any y and get a lower bound this way? I see shaking heads. Why doesn't any old y work? Yeah?
When you did that inequality, you're using all the positive x's every single one.
Exactly, right? So in order to make this inequality work, right, I need coordinate-wise for ya to be less than or equal to c. Okay, otherwise, there's some x's where it might not be true. But as long as ya is less than or equal to c in every coordinate, this is true for all x, and I get a lower bound. Now, this is a technique for coming up with a lower bound. I want the very best possible lower bound. So if I want to write down the problem of finding the very best possible lower bound using this technique, how would I write it down? Well, I would say I want to maximize yb, right? So I want to maximize y times b. But I have to satisfy these constraints that ya is less than or equal to c so that the lower bound actually works. So what's interesting is that I have now constructed a different linear program. Right? My search for a lower bound has produced a different linear program. This is known as the dual linear program. And it's called the dual because it has a very intimate relationship to the original linear program. Okay? But we've already proven something quite nice, which is called weak duality. So our weak duality lemma says that if we have this w, which is equal to the maximum, sorry, max or min, of cx such that ax is equal to b and x greater than or equal to 0, and z is equal to the maximum of yb such that ya is less than or equal to 0, if these are both feasible, then z is less than or equal to w.
UA less than C?
What was that? Sorry. So if they're both feasible, then the dual linear program provides a lower bound on the what's called the primal linear program. And conversely, the primal linear program forms an upper bound on the value of the dual linear program. Okay. Now, this turns out to be just this tip of the iceberg. So now we have these primal and dual linear programs. Next time, we are going to show strong duality, which is that in fact, z is equal to w. These two linear programs have exactly the same value. And that's extremely useful, right? Because you can take a lot of problems and formulate them as primal linear programs, and take their duals and get a completely different linear program, or sorry, not completely different, but a somewhat different linear program that has the same value. And that turns out to be able to give you a lot of useful perspective on the original problem. And in fact, a lot of the most important things that we've shown so far, max flow min cut and feasible prices for convex for min cost max flow, turn out to be just special cases of applying this duality technique. So min cut turns out to be the dual linear program for max flow. And feasible prices turns out to be the dual linear program for min cost flow. And we'll start to dig into that next time. I'm going to hold my office hours today, as usual, but only if somebody tells me that they want to have that. They want to come see me, because otherwise there's a talk I'm going to go to. So if you'd like to see me for office hours, come on down here and tell me, and then we'll go up and talk about whatever. Oh, thank you. There is a talk. Can one of the theory graduate students remember the title? I think it's on constraint satisfaction and the need for high dimensional linear programs to, is that right? It's about the complexity of using linear program to solve constraint satisfaction problems.